So in this first lecture, I'll give an introduction to topological insulators. So this will more or less be the fundamentals going back to basics, and this will set the framework for my next two lectures. So the next lecture will be on topological crystalline insulators, and that will lead into topological quantum chemistry. And then on Friday, on the third lecture, we'll talk about topological semimetals. So, this lecture is, I just want to cite this review article by Hassan and Kane at the bottom. If you're interested more in learning the fundamentals of topological insulators and superconductors, then I strongly recommend this article. So to start off with, in order to contrast a topological insulator, we first just need to mention what is an insulator, as everyone probably knows. So an insulator does not conduct electricity. So I show here some examples of insulators, but from a band structure perspective, an insulator does not have any low energy excitations. And so in other words, there's a gap between the top of the valence band and the bottom of the conduction band. So not all insulators are the same. Of course, this is what we're going to try to do, motivate that there's different types of insulators, including topological insulators. But I wanted to first go back to maybe the most fundamental example of a topological phase, which is the quantum Hall effect. So I just said that an insulator should be something which does not have low energy excitations. And so now if we think about the quantum Hall effect, the quantum Hall effect describes 2D electrons in a strong magnetic field. And what happens is that the magnetic field quantizes the electron motion. And so we end up with this, these series of quantized energy levels. And since these energy levels are gapped, if the Fermi level, so these are Landau levels, these flat bands, and if the Fermi level is between two energy levels, then this fits our definition. There's no low energy excitations. In order to excite an electron, you need to make a jump of a non-zero amount. So this thing should be an insulator. And if we look at the data of the longitudinal magnetoresistance, we see that it is an insulator. On all of these plateaus, we see these regions where the resistance is zero. So that fits with our previous definition. But in addition to the longitudinal resistance, we have the Hall resistance, and this thing is manifestly not zero. And of course, the important feature here is that we can see not only is it non-zero, but the Hall resistance is appearing in these quantized values, which are these steps here. And so these quantum Hall devices seem like they should be insulating because there's no low energy excitations, but actually they are conducting, and we see this from the Hall resistance. So this tells us that there's a different type of insulator, and it also provides our first example of a topological invariant. So a topological invariant is something which is not changed under small deformations. And so the usual example that people show is this coffee cup donut. Each one of these things has one hole in the structure, and this motivates the definition of a genus. So the genus is basically telling me for some object, how many holes are there in the structure, and I can smoothly deform one of these to the other. You've probably seen the animation, but the notion of a genus does not change under this deformation. Well, the Hall conductivity is a more physically relevant example of this. We see the Hall resistance here, and it's sitting on these quantized plateaus, and it stays quantized even though we change the magnetic field, because this x-axis is magnetic field, and it also stays quantized across many samples, which might have, say, different amounts of disorder. So the Hall conductivity is also serving as a topological invariant. It's an integer number. We see it's an integer here because we can map these steps and look where they lie. It's an integer number, and it doesn't change even when the system undergoes these small deformations. Now, we'd like to understand how the quantum Hall effect can conduct electricity, even though there's a gap to excitations. And so one way that we can understand this is if we plot the Landau level spectrum on a system with edges. And so the previous plot of Landau levels, which was just these flat lines, would be for an infinite system. But if we consider boundary conditions, and if we consider, say, hard wall boundary conditions, then these Landau levels must be consistent with the fact, or the energy levels must be consistent with the fact that electrons could not penetrate hard wall boundary conditions. And so what happens is that the Landau levels curve up at the edges of the system. And then in fact, we see that at the edges, the system is gapless, even though in the bulk of the system, there's a gap. And so this is one way to understand how a quantum Hall system can be insulating in the bulk, but gapless at the edges. And we can also understand this from these cyclotron orbits. And so electrons in a magnetic field will move in little circles, but at the edges, these circles will be incomplete. And this creates some extra state along the edge of a quantum Hall system, which conducts electricity. And there's yet another way of visualizing this, which is in some insulating system, there'll be some extra, in the bulk, there'll be a conduction band and a valence band. But if we plot the system on an edge or on a 2D system that has edges, then we'll see that there's this extra state that appears. And so in the bulk band structure, there'd be a gap to excitations from the valence band to the conduction band. But if we plot this on a finite system, there's an extra state which is gapless on the edge. And so I'm drawing these pictures here because later we'll come back to pictures like this, which are called like the surface band structure. So from the surface spectrum, we can understand how a quantum Hall system will conduct, even though it's gapped in the bulk. So this is actually an example of the bulk edge correspondence. This is a pretty fundamental property of topological phases of matter being gapped in the bulk, but having gapless edges. And this is made explicit early on, even before topological phases were in vogue, by this TKNN invariant, which is the initials of the authors in this old PRL from 1982, where they wrote down this expression. They explicitly computed the Hall conductivity, and they showed that actually we can understand the Hall conductivity from a bulk invariant. And so this expression, I'll get to this later, but this expression is in terms of the bulk eigenstates. That's what the U's are. And so the point here is that we're understanding the Hall conductivity from the surface current, but actually you can also compute this same invariant from the bulk itself. And so that's the fundamental attribute of this bulk edge correspondence. The gapless states are on the surface, but in order to predict whether or not there's surface states, we don't actually need to look at the surface. We can compute some feature of the bulk itself. And that's the fundamental nature of the bulk edge correspondence. So this, right now, if you haven't seen this before, this formula is looking a bit confusing. And so what I now want to do, keeping this quantum Hall effect in mind, is to back way up and do some more canonical examples in 1 dimension, and then build up to 2 dimensions, and then give some intuition for why the Hall conductivity might be quantized by using these earlier lower dimensional examples. So I think this expression here is kind of actually more like the end point of the talk, and now we'll back up and see how we can get quantized invariants. So the fundamental starting point that we need is first Bloch's theorem. And so I'm always going to be talking about topological phases in crystals, although there's a very interesting literature now about topological phases in non-crystalline systems. And so the fundamental attribute of crystals is that crystals have translation symmetry. And because of this, there's some translation operator that can use with the Hamiltonian. And so the eigenstates of this periodic Hamiltonian can be simultaneously diagonalized with the translation operator. And Bloch's theorem tells us that we can write these eigenstates as a product of 2 terms. One is going to be some phase, and the other is the other part has the same periodicity as the crystal. So we call this the cell periodic part of the wave function. And all of these topological invariants are going to be computed in terms of the cell periodic part of the wave function. And so probably, as you know, each one of these wave functions, which are eigenstates of translation, are labeled by a wave vector k, and the distinct wave vectors reside in the first Brillouin zone. So I'm drawing the first Brillouin zone here in 2 dimensions. Kx goes from -π to pi, ky goes from -π to pi, and we should equate pi and -π so that the square actually has the topology of a torus. And then in order to understand the properties of some material, we'll plot the eigenstates of these eigenvectors, and this gives us a band structure. And so this is just some schematic band structure, which I've drawn here, which is just energy eigenvalues as a function of this wave vector. The important point is that we need to have a notion of what it means for band structures to be topologically equivalent. So I already mentioned that a topological invariant is something which remains unchanged to smooth deformations. So what is a smooth deformation of a band structure? A smooth deformation of a band structure is moving the bands around, and a non-smooth deformation is when bands cross. And so if we start with, say, a band structure of some atomic insulator, so we assume that our atoms are very far apart from each other and the bands are completely flat, there's no hopping between atoms. Then a smooth deformation is that we slowly introduce some hopping terms, and we would say that these structures are all topologically the same as each other. And what would not be topologically the same is if this band gap closed and two bands crossed and reopened, and that would be a topological phase transition in the band structure. So the important notion that we need to diagnose topological phases is the Zac phase. So the Zac phase is just the Berry phase around closed loops in the Brillouin zone. So you've probably seen Berry phase before in the context of varying some parameter in the Hamiltonian and seeing how the eigenstates change as you vary that parameter. Here, we're going to do the same thing, but that parameter is this wave vector K. So with that in mind, we can define the usual notions of Berry connection and Berry phase. So the Berry connection is just the overlap between one of these cell periodic parts of the wave function u and the derivative of u. So we usually write it in this way, and we usually call it u du. And then the Berry phase is just the integral of this Berry connection over some closed loop. And the fact that it's a closed loop is important because that's what makes the Berry phase path independent. If it wasn't a closed loop, then you could choose different paths with the same endpoints, and you'd get a different Berry phase. And this is also the reason why you might wonder, could we write down the same expression with the full block eigenstate instead of just the cell periodic part u? And the answer is not really. It wouldn't be well defined because the full wave function had an extra phase e to the I kr. So if we take the derivative of that with respect to k, we'll pull down a factor of r, and then integrating this thing will end up diverging because r is spanning the entirety of space. So it's actually very important that we use this cell periodic part of the block wave function to compute Berry phase and other topological invariants. Okay, but as you know, there's some ambiguity in the phase of a wave function. So for any wave function u of k, we can always add some phase to it. And this phase will also translate to an extra term in the Berry connection. And this extra term in the Berry connection will also translate to an extra term in the Berry phase. And so if we look at what this extra term in the Berry phase is, we see that it's an integral of a derivative of phi. And so this integral of a derivative, you might think since it's over a closed loop, it has to be 0, but actually it can be a multiple of 2 pi because over a closed loop, the phase is only defined mod 2 pi. So it doesn't need to come all the way back to itself. It can come back to itself mod 2 pi. And so this wave function phase ambiguity is why the Berry phase is only defined mod 2 pi. And this actually makes sense. This is why we call it a phase, because most phases are defined mod 2 pi. So this is important, but not that surprising. And finally, I should mention the Berry curvature. This thing is the curl of A, and this is actually gauge invariant because we see if we plug this extra term into the Berry curvature, the curl of the gradient will disappear. And so Berry curvature is gauge invariant, but all of these other quantities are gauge dependent. The Berry connection is gauge dependent, and the Berry phase is only defined mod 2 pi due to this gauge choice. So the special thing, one special thing is that in one dimension, the Berry phase gives a polarization. And so we can just the normal polarization that you're familiar with. And so the way to understand this, well, first off, let me simplify this expression for Berry phase to one dimension. In this case, there's only one k variable, and the closed loop that we're integrating around is just the entire Brillouin zone. So 0 and 2 pi are identified, so the Brillouin zone is just a circle. And so the Berry phase is integrated over that circle. And so we can heuristically understand why this Berry phase would give us polarization, because we can make this canonical substitution that I partial k can be replaced by x, just like I partial x can be replaced by k. And so with that substitution, we can kind of see that this integral is really the expectation value of the position operator x. And that's exactly what the polarization is. The polarization in a continuous system would be integrating over all degrees of freedom, and then computing the charge at each of those points. And so the polarization has this extra factor of E out front for charge, and then it's just integrating over all the degrees of freedom and taking the expectation value of position at all those points. So the Berry phase in one dimension gives us the polarization along that dimension, along that direction. And so now you might think that there's some ambiguity because I just said that the Berry phase is only defined mod 2 pi, but it seems like the polarization is something that should be well defined. And the resolution of this is that the polarization for an infinite crystal is only defined mod E. It's actually not well defined. Well, it is well defined, but only up to the electron charge. And the reason for this is that for an infinite system, it's not clear. There's multiple choices of unit cell that you can choose. And so, for example, this is a very simplistic system that I'm drawing here, which would just be an infinite line of positive and negative charges. We could choose a unit cell like this that has a negative charge to the left and positive to the right, or we could choose the opposite unit cell. And if you compute the polarization for either of these choices of unit cell, you'll see that one gives you a polarization of E over 2 and the other minus E over 2. So the polarization will differ mod E depending on which unit cell that you choose. And this is exactly consistent with our Berry phase being defined only mod 2 pi. So there's no inconsistency here. And so we can firmly say Berry phase in 1D gives us polarization. And then we can also, so the polarization of an infinite system is only defined mod E, but actually differences in polarization are well defined because if we compare, so suppose we have two different systems, but we can tune from one to the other by some parameter in the Hamiltonian, then we can write down the difference in polarization. And if we go through these steps, plugging in the polarization formula and taking this derivative, we'll see that ultimately through a little bit of algebra, difference in polarization can be written as the curl of A, and this quantity is gauge invariant. So, so the main point is that we can understand differences in polarizations in a concrete way, even though the polarization itself for an infinite system is only defined mod E. And this connection between Berry phase and polarization is now known as modern theory of polarization. And these are some of the early papers introducing this concept. So now I want to give a little example, which is kind of the canonical example of a 1D topological phase. Later, we can come back to the question of whether we should call this thing topological or not, but it's certainly called topological in the literature. So this is called the Sue-Schrieffer-Heeger model, or usually known as the SSH model after these authors. So the model is as follows. This model is meant to describe polyacetylene, which is a chain of carbon atoms. Question?
Yes, I have a question. I think it's good to do it now. Is the Berry phase only different to zero only in polar systems?
Is it only different from zero in polar systems? Right, exactly. So yeah, that's exactly it. So the Berry phase gives the polarization. And so if you have some system which does not have a polarization, which would mean that the electron charge is located exactly on the atom charge, then this thing would have a Berry phase of 0. And so one way that we can understand how to get a non-zero polarization is that if your electron charge is not sitting exactly on your atoms, but has moved over some amount, that thing will give you a polarization, and that will give you a non-zero Berry phase.
Okay, and there is another question. In a strongly related system whose quasi-particles have a fractional charge, is the polarization only defined mod E2?
Okay. This is an interesting question on many levels. So I should say that right now I'm only talking about band structures. So the theory that I'm describing does not really apply to strongly correlated systems. However, due to this, the statement which holds all the time in all situations is that the polarization, it's really a polarization density, but because the full polarization would be infinite for an infinite crystal. anytime you have an infinite system, there's ambiguity in this notion of what the polarization per unit cell is because of this choice. And so if you work this out for yourself, you're familiar with the fact that for a charge neutral system, the polarization does not depend on the choice of origin. Okay, fine. But now you can also, if you kind of repeat the same calculations for some infinite crystal, if you compute polarization density, you'll see that depending on density means polarization per unit cell, and you need to define your unit cell. And it's not always clear what the unit cell should be. And these different choices of unit cell, you can see that if you shift by a full lattice vector, one of the atoms in the unit cell, you'll change your polarization mod E. So in strongly correlated or any system, polarization density of an infinite crystal is only defined mod E.
Okay, thanks. That's all.
Yeah, great. Yeah, please feel free to ask questions anytime. Okay, so I was going to give this example of the Ssh model. And so what this model is, these blue dots are meant to be carbon atoms. And the point is that, let's see, there's all these hydrogen carbon bonds. And because of the number of electrons floating around, these carbon atoms could make single bonds or double bonds. And so if we wanted to write down a Hamiltonian for this system, we would write down some hopping amplitude to get from, I'll call these A and B sites. So to get between neighbors, there's some hopping. But if you have a single bond or a double bond, it'll make the atoms a little bit closer to each other or a little bit further from each other. And so this hopping should not be the same between all the atoms. Between some of them, it'll be a little bit weaker, and some of them it will be a little stronger. So in tight binding language, we can write this down as some Hamiltonian, which has a hopping from A to B, and then a hopping from B to A. And these things will have a magnitude average of T, that's just the hopping parameter, but plus or minus this small parameter delta. And depending on whether delta is positive or negative, we interpret that as either having single bond, double bond, or double bond, single bond. So there's these two different possible configurations. And so we can plot the energy spectrum for both of these cases. And what we see is that the energy spectrum has a gap, and that gap is proportional to the size of delta. Now, in these two different systems, the electron charge in the ground state is localized more strongly on the double bonds. And so if we think of just one free electron sitting in the valence band, if we compare these two structures, in one case, the electron density will be more localized, say on this double bond. In the other case, it will be more localized here. So there's a shift of electron density by half a unit cell. The full unit cell has two atoms. And so, so we can see that if we change the sign of delta, we'll change the polarization because we're changing where the electrons are located. We'll change the polarization by half a unit cell, so E/2. And due to this relationship between polarization and Berry phase, there's a shift in the Berry phase between when we change this sign of delta between these two different phases, there's a shift in the Berry phase. The Berry phase shifts by pi. And so this is actually, with the appropriate symmetry, the Berry phase is actually fixed to either be 0 or pi. You need to have inversion symmetry to do this. And so this is actually the simplest example of a topological transition. These are both insulating phases. And as we, if we change delta from positive to negative, we'll have to close the band gap and reopen it to get from one phase to the other. And when we do that, the Berry phase will jump from pi to 0. So this thing constitutes a topological transition where the topological invariant is given by the Berry phase. And physically, we can understand this Berry phase. The difference between the two phases is that the polarization is, the electrons are basically moving by half a unit cell. Just to say, there's an alternative explanation of this Berry phase. All the physics is the same, but we can understand this as a winding number. So I'll just explain it lightning fast. We can write this Hamiltonian on a basis of Pauli matrices, which act on the A or B atom in the unit cell. And like I said, we need some type of symmetry here, say inversion symmetry. With the right symmetry, this Hamiltonian only has sigma X and sigma Y matrices. And so you can define some winding number, which is if you take the coefficient of sigma X and sigma Y, how does that coefficient change as K winds around from 0 to 2 pi? And the winding number will either be 0 or 1, which corresponds to this Berry phase of 0 or pi. But the other thing I want to say about this model, so this is a 1D topological phase transition. And we said earlier that one of the defining attributes of a topological phase should be a bulk edge correspondence. So how do we see that here? Consider a boundary between these two different phases. So one of these is going from single, double bond, and then it switches double, single. So there'll be some boundary here. And what happens is that at this boundary, there's an accumulation of charge. And so we can see that there should be some extra electrons sitting at the boundary, and that's the bulk edge correspondence. And so we can actually work this out explicitly. You can look at these slides later and work it out yourself if you haven't done it before. But if you take the Hamiltonian on the previous slide, we want to write down a low energy theory. So we should expand around the smallest place where the gap is the smallest, that's around k equals pi. And we also have to expand around this parameter delta being small just to get a simple theory. And then the Hamiltonian becomes greatly simplified, and it looks like this in terms of the sigma x and sigma y matrices. And so then to get this domain wall between these two regions, we should set this parameter delta to be spatially dependent. So on one side, it will be greater than 0, and on the other, less than 0. So delta should look like this. When we do that, this Hamiltonian is no longer translationally invariant because it has this defect. And so instead of writing k here, we replace k with minus I dx. With all those substitutions in place, you can actually exactly solve for a 0 energy eigenstate. This is the solution. It's localized at 0 energy, so right in the middle of the gap. And it's also spatially localized. It's localized at x equals 0 right at this domain wall. And so if you plot this state, if you plot this wave function magnitude squared, you'll see that it's exponentially decaying, but it's localized right on the boundary, and its energy is in the middle of the gap. And so this is an example, kind of the earliest example of the bulk edge correspondence. It's a surface state or a domain wall state between these two different phases sitting in the middle of the energy gap. So now we can take this same logic and go up one dimension. So this next example is called the Phallus charge pump. So now we're going to keep our 1D system, but add time. So what am I drawing here in this picture? I'm trying to draw a bunch of positive charges. These would be the atoms in our one-dimensional system. And then these minus charges would be electrons or electron wave functions where they're localized. And so imagine some system where we change some parameter in the Hamiltonian and we cause the electron charge to move. So this would be at time 0. And then at some later time, the electron charge has moved over by half a unit cell. That would be like moving between these two phases of the SSH chain. So the polarization is changed by E/2. And then we keep going. And at some final time, which I call capital T, the electrons have moved over by an entire unit cell. And so in this process of charge pumping, the initial and final configurations are completely the same, but something has changed because the electrons have moved over by half a unit cell. And notice that the initial and final configurations are only the same in an infinite system. In any finite system, there'd be a little bit of a lag, like in my picture, where there'd be some charge left over. But in an infinite system, we can't tell the difference. But what is well defined is how much the polarization has changed. And so we can ask the question, how much charge is pumped in one full cycle? So as we go from time 0 to time t, what happened to the electron charge? And so we can compute this as the change in polarization. We can say the change in polarization is given by the integral over time of the derivative of the polarization. So that will give us P final minus P initial. And then we can plug in our definition of polarization. And as we saw before, see that we'll get the curl of the Berry connection. But we also know the answer, how much charge is pumped. There's just one electron, because what we've done here is we've moved the electrons all over by one unit cell. And so we can see here that since we know the change in polarization is 1 electron, it must be that this integral here is giving us 1. And if we say we pumped our charge twice as fast, as long as the initial and final configurations are the same, we could only get some multiple of one electron here. We could never get a fraction as long as the initial and final configurations are the same. So this integral, no matter what our pumping is, this integral must give us an integer. And this integer is what's known in condensed matter as the Chern number. So this is the same integer we'll see momentarily that comes back to the quantized Hall conductivity. So formulaically, this is the definition of the Chern number. And although this is a complicated looking integral, it always has to give us an integer. And one way to think of it is to think of this charge pump system. As long as your initial and final configurations are the same, then you can only have pumped an integer amount of charge. And so the takeaway, or what I want you to take away here, is that the Chern number is some topological invariant given by this formula. It always gives us an integer, and it characterizes wave functions in 2 dimensions. And so in this case, our 2 dimensions are our 1D system, so K, and time. But in the quantum Hall case, those 2 dimensions will be 2 spatial dimensions. And if you know your wave function, this is something that you can just compute. It may not always be easy, but you just have to compute this integral. It's something concrete. So the Chern number is some 2D topological invariant, but I think for me, it's helpful to think of this as how much the Berry phase winds. And so if we take apart a little bit more of this formula for change in polarization, we can write this as the integral in time over the derivative of the Berry phase with respect to time. And so integral of derivative just gives us the Berry phase at time t minus the Berry phase of 0. We kind of knew this because change in polarization should be proportional to change in Berry phase. And so this actually gives us a practical way to compute the Chern number, which is very convenient numerically. Instead of doing that integral that I showed on the previous slide, what you do is you compute the Berry phase, say at some time, and then plot that Berry phase as a function of time. And you can see a Chern number of 1 means that the Berry phase, instead of returning to its original value, say goes from 0 to 2 pi. So this is a practical way to compute the Chern number by thinking of it as a Berry phase in one direction, plotted as you move some parameter in the other direction. And just for comparison, I want to show what the trivial case would look like. So a Berry phase of 0 would mean you make the same plot, but you come back to your original starting point. There's no winding around. And similarly, if there is a Berry phase of 2 or winding of 2, this would mean you go around twice, etc. And so this is, like I said, a practical way to compute the Chern number. And if you're wondering how to rigorously define winding, what you can do is just draw a straight line across here. And you can see that if you draw a straight line anywhere in the spectrum, the number of times it crosses a band with positive slope minus the number of times negative slope will give you this winding. So here we cross 2 lines, so that gives us a winding of 2. But here we wouldn't cross any, so we could get a winding of 0. Or if we drew a line down here, we'd say we cross positive slope and negative slopes. That's also a winding of 0. So no matter how complicated this plot is, you just draw a straight line across it, count how many bands are crossing with positive and negative slope, and that's a way to get the Chern number. So now we can come back to this quantum Hall physics. And so we can understand the integer quantum Hall effect through what's known as this Laughlin flux argument. So this is how the argument goes. And what we're going to try to do is show why the Hall connectivity has to be quantized. So the picture is like this. This 2D cylinder is our quantum Hall system. So remember, quantum Hall is describing 2D electrons in a magnetic field. And so now we're going to take that system and wrap it into a cylinder. And then we're going to thread some magnetic flux through the center of the cylinder. And so you might be worried, our initial quantum Hall system was 2D and it had the magnetic field perpendicular. In this new configuration, the magnetic field is not perpendicular, it's going through a hole in the center, but we could make the same argument by taking this cylinder and kind of flattening it out, and then the magnetic field would be going perpendicular through a hole in the center. But ultimately, we're making a very fundamental argument here for why Hall connectivity should be quantized, and the geometric configuration doesn't affect that argument. Okay, so let's go on. So the idea is that we're threading a flux quantum, 1 unit of magnetic flux. So at time 0, there's no flux, and at some final time t, there's exactly 1 flux quantum going through the center of this system. So by Faraday's law, we know that there's going to be some EMF, electromagnetic force, which is when you have a changing magnetic field, which is changing in time, there's going to be an EMF around this. And that change in potential is going to generate an electric field. So there's some electric field which is going around the cylinder. And then by definition of the Hall conductance, the Hall conductivity tensor is relating how much current you get along the cylinder related to the perpendicular electric field, which is now around the cylinder. And so if we plug in this expression for electric field, then we see that by definition of the Hall conductance, we get that the current density is given in this way, and it's related to the time derivative of the threading of this flux quantum. And so then we can ask, how much charge is moving from the left to the right-hand side of the system as we thread this flux quantum? Well, current is going along this way, and current is carrying charge. So we can say the change in charge, which is the total charge pumped from the left to the right side, is given by the integral of current over time. And since the current is given as the derivative of the flux through the cylinder, we can plug this expression for current into here. And then we see that the total charge which is pumped is proportional to this Hall connectivity tensor, and the constant of proportionality is this quantum of h over e. So this is all just plugging in formulas carefully. And then finally, there's some final step, which is that if we assume that the system is insulating, then this process of threading 1 flux quantum, we can always gauge away 1 flux quantum. So the eigenstates must be exactly the same at time 0 and at time t. Maybe now you see the comparison to this Phallus pump. We did some procedure, but at time 0 and time t, capital T, the system is exactly the same. All the eigenstates are the same. So the only thing that can change in this process is that the occupation number of these eigenstates can change. And the way that occupation number changes is that some charge on the left-hand side is now moved to the right-hand side. But since all of these states can only host either 0 or 1 electrons, we must conclude that the total charge pumped must be an integer number of electrons. We don't know what that integer is, but it must only be an integer. And so that tells us that this change in charge, the left and the right-hand side, must be an integer number of electrons. And so then if we relate these two expressions, we can see that the Hall connectivity is an integer multiple of this quantum e squared over h. And so through this argument, which relies only on gauge invariance, we see that if we have an insulating system, the Hall connectivity is restricted to taking integer multiple values of e squared over h. And this explains the quantization of the integer quantum Hall data that I showed at the beginning. This is valid for any insulator. So in some system without a magnetic field, this integer n could be 0. And then as we vary the magnetic field, that changes the Hamiltonian, and that changes this value of n. But the logic here is showing that n must take on integer values for any insulating system. And so now we can compare this to the TK and N invariant that I showed earlier. And then what we have to deduce here is that this TK and N invariant, if we write that formula, so the formula there was written in terms of the cell periodic parts of the block wave function u, but if we translate all those derivatives, we can see that we can write that as the curl of the Berry connection. And so, so that TK and N invariant has to be quantized by the logic that we've just been talking about. The curl this integral of the Berry curvature always takes on an integer value. And so now we have two ways of understanding this. We have this Laughlin flux argument, which uses gauge invariance and says that Hall connectivity has to be quantized. And then we also have this explicit calculation by TKNN, which amounts to some integral, and that integral also has to be quantized. But the integral gives us a concrete way to compute the Hall connectivity. This Laughlin argument just says it has to be quantized, but you won't know what value it is until you actually compute this thing. And so this, to make the connection to the Phallus pump, that churn number that we saw in the Phallus pump argument, which is as a function of the 1D wave vector and changing the Hamiltonian in time. Now here we have a 2D system. And so the churn number is actually in momentum space. That two parameter system is kx and ky. And so we can think about if you computed a Berry phase, say around the ky direction, and looked at how that Berry phase changed as you vary the starting point kx, you would see some change in Berry phase, and that change in Berry phase would give you a churn number in the way that I was just showing on the previous slide. So coming back to the bulk edge correspondence, the churn number gives us a surface state, and we can understand this. In different ways. We can compute the TKNN invariant in the bulk, or we can look at the surface states. And in the end of the day, we'll get some plot like this, where we see, like I showed earlier, there's one extra state connecting the valence and conduction band if we plot our band structure for a finite size system. And so since that state does not appear when we plot the band structure in a bulk system, we deduce that this state has to be localized on the edges. And the other thing that I want to emphasize in this bulk edge correspondence is that frequently this is drawn straight, but it's not, in reality, it's not going to be some straight line connecting the conduction and valence bands. It can have some curvature, and it can even go up and down like this. So the actual dispersion of a surface state is determined by surface physics, but the bulk edge correspondence tells us that there has to be some state which is connecting the valence and conduction band. If you have a churn number of 1, if you have a churn number of 2, there'll be 2 states, etc. So then in the last couple of minutes, I just want to say how this extends with time reversal symmetry. So time reversal symmetry is some anti-unitary symmetry, which will, it commutes with the Hamiltonian, but if we diagonalize the Hamiltonian with respect to these block wave vectors k, it takes a state indexed by k to a state with minus k. And it also has this property that the time reversal operator squares to -1. And so this means that at every k, which is the same as minus k, so i.e. k equals 0 or k equals pi, these are known as the time reversal invariant momenta, there has to be 2 degenerate states, which is a state and its time reverse partner. So from this logic, we can immediately see that time reversal symmetry is inconsistent with having a churn number, because we just said that a churn number should give us a surface state like this, but time reversal symmetry would require at k equals 0, there has to be a partner like I've drawn here. And so having a churn number is inconsistent with time reversal symmetry. And actually we could see this because if we computed the action of time reversal on the Berry curvature, we would see that it's odd. And so if we integrate the Berry curvature to get the churn number in the presence of time reversal, that integral must be 0. So the bottom line is that in the presence of time reversal symmetry, you can't have a single surface state, but you can have surface state partners. And this is exactly the definition of a 2D topological insulator. So in a churn insulator or quantum Hall state, you'd have just one of these chiral edge states or multiple. But in a topological insulator, you have states which are moving in opposite directions, and they can't gap each other because they're time reverse partners. So time reversal symmetry is protecting them. And so this gives us a notion of what's called a Z2 topological invariant, which is we can ask, are there an even or an odd number of bands? So I said before, to compute the churn number, we could draw a straight line across, and we could see how many bands are we crossing with positive and negative slope. Well, if you have time reversal, you'll always cross an even number of bands, and you'll always get churn number 0. But you could make a modification, which is to just look at half the Bruin zone, because if you have time reversal symmetry, k and minus k are related. So if you just look at half the Brillouin zone, then you can just count the number of states which are crossing some line over half the Brillouin zone, and you can ask if there's an even or an odd number of those. And if there's an odd number, then that means you have a 2D topological insulator. And so similarly to this TKNN invariant, there's also a bulk invariant to compute this the Z2 TI index. But similarly to the TKNN invariant, it's very hard to compute. So this is the explicit formula. You can see it's written in terms of these cell periodic wave functions, but in practice, it's ideal to avoid computing this invariant. So I guess what I want to emphasize is we can compute, or we can classify 2D TIs by their surface states, but in practice, we don't actually want to compute those surface states. We want to compute things in the bulk because that calculation is computationally simple. So we have this bulk invariant, but it turns out that this is quite difficult because you need to choose a continuous gauge across the Brillouin zone. And so there's, again, a practical way to compute this Z2 invariant, which is to compute the winding of the Berry phase. So I previously showed to get the Chern number, you could see how does your Berry phase wind as you vary some other parameter. But here, what we want to do is look over half the Brillouin zone. So say take the Berry phase going from 0 to pi, or in this case, minus pi to 0. And then we can ask the same question. If we just look over half the Brillouin zone and draw a straight line, how many times do we cross this Berry phase? If we cross it an odd number of times, then we have a 2D TI. And if we cross it an even number of times, like on this right-hand plot, which could be 0, or it could be crossing twice, then we have a 2D trivial phase. So this is one practical way to compute the Z2 invariant. And I also just want to point out that I've kind of gone back and forth between plotting the Berry phase winding as a function of some parameter and plotting the surface states. And actually there's a rigorous connection between these, which is outlined in this paper, in this reference.
Jen?
Yeah?
I have 3 questions.
Great.
Okay, so the first one from Mark Villa. You mentioned in the 1D case that only when the unit cell is not polar, the Berry curvature is finite. Does this apply also in 2D and 3D?
Right. So the Berry phase in this is kind of it's a 1D result because you're always going to compute the Berry phase in one direction. And that will give you the polarization in one direction. But yes, if you computed the Berry phase in X and then computed it in Y and then computed it in Z, same thing. You could get the polarization in all those directions. They would just be computing Berry phases in different directions. The Berry phase has an orientation because you're making a closed loop in momentum space, and you need to choose whether that loop is going to be going around X or Y or Z. So it generalizes to 3D in that way.
Okay, then from Richen Chion, when we calculate the Hall conductivity, we calculate the Chern number of the bulk band. Why don't we need to consider the Chern number of edge state dispersion?
Right, exactly. So that's a good question. This is the whole point. This is the whole point of the bulk edge correspondence. So the Chern number is defined for a 2D system with two parameters that we can make closed loops around. And so that necessitates periodic boundary conditions in those 2 parameters. So I would say the Chern number is something you calculate for 2D bulk. By bulk, I'm meaning of a 2D material. And the edge state dispersion is a consequence of that. So there's 2 calculations you could do. One is Chern number in the 2D bulk, and the other is plot the edge band structure and look for edge states. But it doesn't make sense to compute the Chern number of the 2D edge because the Chern number requires 2 periodic directions. And once you make a finite edge, you don't have 2 periodic directions.
Okay, and then from Umesh, can you repeat the last point again about topological insulator having surface state protected by time reversal symmetry?
Yeah, so right, let me just say, there's 2 points I'm trying to make. One is that if you have time reversal symmetry, you can't have a Chern number. But if you have time reversal symmetry, you can have something enhanced, which is you can have 2 surface states. Ordinarily, if you had no symmetry at all and you had 2 surface states, these things could gap. But time reversal symmetry protects this gap from opening. because the two states here are time reverse partners. So they're related by symmetry. So you can't change one to one energy and another to another energy. So, right, so that's the point, that time reversal symmetry has the capability of protecting surface states which cross. And if you didn't have time reversal, this would generically gap. And the overarching feature here is that symmetries can protect surface states. And so if you add more symmetry, then you can get enhanced or different classifications.
And the last one is something that I think you explained already, but it's from an anonymous attendee. What is the difference between Zac and Berry phase?
Yes, good. So the Zac phase is Berry phase over the Brillouin zone. So Berry phase is a very general concept, which is how do wave functions change as you vary some parameter. Zac phase was just to say, look, that parameter that we vary can be k, the wave vector. So instead of varying some external object, you have some Hamiltonian, it's a function of k, and you treat k as a variable, and then you can make a closed loop around the Brillouin zone. And it's closed because you can go from 0 to 2 pi, and those points are the same. So yeah, Zac phase is just Berry phase around the Brillouin zone. And much of the time, people just call it the Berry phase if the context is obvious.
And the last one. Are these last plots of Berry winding numbers the same as Wilson loops?
Yes, these are exactly the same. So, right, so I think that TDIS is going to cover this later in the week. But yes, this is the exact same thing as a Wilson loop. And just to say, for people who are in the know or have seen this before, there is one little thing which I swept under the rug here, which is actually we've been talking about the Berry phase just for one band, which is like UDU. If you have multiple occupied bands, which you always do for a TI, then that Berry connection should become a matrix. It'll have indices that depend on the band, the occupied band. So it would be like UN, DUM, and that will give you what's called a non-abelian Berry phase. And that will give you Wilson loop plot with multiple lines like this. So yeah, I'm not going to say anything more about it, but the answer is yes, those things are the same. Good. So let me just show a couple of more slides so we don't run over too late. So the other thing that I want to say here is that if you have extra symmetry, it's even easier to compute the Z2 invariant. So there's two cases that I want to mention. One is quantum spin Hall, which is if you have spin conservation, if your two spins don't mix in your Hamiltonian, you can compute Chern number for spin up and Chern number for spin down. And that will give you the Z2 index in that special situation. The other situation, which I'll talk more about tomorrow, is if you have inversion symmetry, then you can compute the inversion eigenvalues at these trim points. And this is actually the method which is used in practice the most. Instead of computing that more complicated formula that I showed, you just look at all your trim points and compute the inversion eigenvalues and multiply them all together. And since inversion eigenvalues are either even or odd, +1 or -1, their product is also +1 or -1. And if that product is -1, then you have a non-trivial Z2 invariant. So let me just skip ahead to kind of the last thing, which is that in 3D, what's the analog in 3D? In 3D, it turns out that you have 4 Z2 indices, which are called strong and 3 weak. And this corresponds to having a Dirac cone on the surface if your strong index is 1, or for your weak indices, you have 2 Dirac cones on the surface. And we can understand this, what's called a weak 3D TI. If you stack a bunch of 2D TIs, each one in this stack will contribute a surface state. And so you'll end up with multiple Dirac cones. But this thing requires translation symmetry. If we broke translation, which would cause us to fold the Brillouin zone, then these Dirac cones would gap each other. And so that's why these are called weak indices. The strong index doesn't have that property because it's 1 Dirac cone. So you can't gap it by breaking translation symmetry. And one way to think of this in an analogous construction is that if you have a KZ = 0 plane to be a 2D, say a 2D TI and the other planes to not be, then this would give you the appropriate surface states, but it manifestly doesn't really have anything to do with translation symmetry. So the slides that I skipped are having to do with experimental realizations. You know, so you can look those up and look back at these slides and look up those references. But the last thing that I want to say is that, because this leads into tomorrow, I've talked about churn number, which requires no symmetry, and time reversal symmetry, which gives us 2D and 3D TIs. What else is there? Well, the famous classification of these is called the tenfold way classification. The classification is quite technical. You can look at the reference here, but the point is that topological phases in any dimension with either time reversal or charge conjugation, which is particle hole symmetry, or both or neither, these have all been classified. And so just to show some examples, these are the examples we talked about. So there's these different symmetry classes which tell us, do I or do I not have time reversal? And if I do, does it square to +1 or -1? And same with charge conjugation. There's 10 combinations of those. Class A has no symmetry. In 2D with no symmetry, we have a Z invariant, and that's our integer quantum Hall invariant. If I look at this class A2, which is the class of time reversal symmetry in electrons, if I look at 2 and 3D, I get this Z2 invariant. So, so these are the 2D and 3D TIs that I mentioned. And all these other classes are about topological superconductors, and some other classes. All of these are with on-site symmetry. And so tomorrow, what we'll talk about is adding crystal symmetry and see how that enhances classification. Okay, so that's everything I want to say for now. Maybe there's time for 1 or 2 questions, or maybe we should just put it on Slack. That's up to you guys, Maya.
No, sure. There is one question from Chiara. Can the Wilson loops always detect topological edge states?
Great question. So like I said, there's this correspondence between the Wilson loop spectrum and edge state spectrum. So for 2D TIs and you know, some other examples, then the Wilson loop spectrum can tell you about the edge state spectrum, and that's robust. Once you start adding crystal symmetry in, it becomes a lot more complicated. It's not, for some cases, it's not always clear what the right Wilson loop calculation would be. And also it's not clear that you would have surface states. So maybe I answered I think the answer to your question is that yes, the Wilson loop spectrum is in topological correspondence to the edge state spectrum. But in either case, the Wilson loop or the edge state spectrum doesn't always tell you the nature of topological states with crystal symmetry, but yes, they do always correspond to each other.
Okay, and another question is, could you please elaborate on your comment on the topological nature of the SSH model?
Yes, right, I can elaborate on that. So one of the things that I'll mention tomorrow, so I won't bother skipping back to that slide, but the comment that I made earlier was that should we call the SSH model a topological phase or not? And these churn number phases and 2D and 3D TI phases, one of the things that makes them topological, I would argue that this is the definition of a topological phase, is that you cannot deform that phase to an atomic insulator. If I try, it's an insulating phase, but if I tried to say pull atoms apart and make a model with completely trivial flat bands, I wouldn't be able to do that because those phases lack exponentially localized Wannier functions. They're completely unvannierizable. There's something different about the SSH chain, which is in 1D, there's 2 different models, delta greater than 0 and delta less than 0. And each one of those is actually an atomic limit. We can think of it as having electrons situated in one spot, but the difference between the 2 models is that in one case, the electrons are at x equals 0, and the other, they're at x equals 1/2. So there's no notion, like electron Wannier functions exist and are localized in that model, but the 2 models are different. And so I would say that that's a topological phase transition because there's a quantized invariant, which goes from 0 to pi, but neither phase is actually a proper topological phase because it can be thought of as a band insulator. It has exponentially localized Wannier functions. And actually, this should be, in one sense, it's a little bit obvious because changing delta from less than 0 and greater than 0 is a translation by half a unit cell. So there's no notion in which these things are, there's no way one could be topological and one couldn't, but the transition between them changes this very phase invariant.
Okay, on the last question, following the Wilson loop, its correspondence, does this mean that if a system has a Wilson loop that has no gap, it will have a topologically protected edge surface state?
Right. So there is one subtle thing in this, which is that these the Wilson loop surface state correspondence is they don't need to be exactly the same, but they need to be topologically the same. So what that means is that it would be possible, like for example, let's look at this picture on the right. The Wilson loop shows gapless state here and gapless state here. The surface spectrum might not have this surface state because this state, it might be moved up. You know, suppose this was a band structure and suppose this was the valence bands and this was the conduction bands. In the edge state spectrum, there's nothing that pins this to 0. So these states could be way higher in energy and therefore completely disappear. So there's not a one-to-one correspondence, but there's not an exact correspondence, but there's a topological correspondence. The topological attribute in this picture is that if I draw a line from 0 to pi, I will cross the edge states an even number of times, which may be 0 or it may be 2. That's what the correspondence is. But it may be possible that the Wilson loop spectrum has a gapless state, which is not present in the electronic edge state spectrum because there's nothing that fixes the edge states to a particular energy. Yeah.
Okay. Thank you, Jen. Okay, so we take a break and we reconvene at 5 p.m. Central European time, 11 a.m. in New York, I think. Okay, see you in the 20 minutes. Thank you, Jen.